Hello, I'm making our coronavirus updates now every other day. I've noticed that I think it's a little too much information for people these days, and I think you want to see positivity in addition to all the negativity. So I didn't post yesterday. I'm still collecting the data, but I'm posting today. Luxembourg still has a very high prevalence per 100,000. Again, population density is very high there. The area is very small, but that's how you breed these diseases. Switzerland is following that. Spain, Italy's moving down to fourth. Italy's starting to go down a little bit here. Change from yesterday. You still see an increase, about 4 people per 100,000 in Italy. Huge increase in Luxembourg. Going to the United States, we're at about 70 people per 100,000. Increase of 8 people per 100,000 from yesterday. And then if you look at the chance of dying if you're in the US, it's about 2.5% if you're sick. So that's because we're having more cases now and there are more deaths. You'll see more deaths coming up, and it's not something that we obviously want, but it'll just happen. It's inevitable with this many people being sick, particularly because of the population density we have. UK is about 9% right now, probability of dying if you are sick. So Ecuador is about 4. So there's creep happening here, creeping up a little bit. Let's look at some figures. So you can see we're still having this upward trajectory in the US right now with cases per 100,000. Just as overall news. Again, it depends on what your location is. And here we have this comparison between Italy. You see that Italy's starting to flatten out a little bit, which is nice for them, but they've had so many cases and they're testing so much. Hopefully their quarantining is working. We're still on the increase, and South Korea is going pretty seriously down right now. So that's, again, remember we started the same date with South Korea and the US. This is my figure that I like showing about what the impact of proportion of individuals above 65 is, 65 or above in a country, and this is the case fatality. So case fatality is the probability of dying if you're sick. So you can see that if you're confirmed sick. You can see that where there are, and this is the line for hospitals per 1,000 people per country. So they tend to mirror each other for most cases, as does population density. This is population density here. And I use this 4-level variable where 0 is up to 100, 1 is 100 to 200, 2 is 200 to 300, 3 is above 300 just to make sure that the population density figure can fit inside this graph here. But there's a mirroring of these three, but the greatest number of deaths or probability of dying is due to this wide chasm right here, right? You see it? Between the proportion of individuals above 64 and hospital beds and availability of hospital beds. In this figure, I plot this ratio that I created, which is the ratio of hospital beds per 1,000 to proportion of the population above 64. So this is a ratio. And then this is the case fatality. It seems to be a pretty good relation here. So the higher this ratio, the lower one's case fatality. So this is basically indicating that the greater the number of hospital beds relative to the proportion of individuals above 65, the better one is to prepare for this horrible outcome. So what I did was I ran a regression. I'm starting to run these regression analyses, and this is using this Andrew Hayes process package, which is an add-on to SPSS, and SPSS is a statistical computer package. SPSS stands for software for, I think it's software for SPSS, statistical software for the social sciences or something like that. I can't remember now, but I know it has social sciences in it somewhere. So this allows me to run an analysis with interactions in it. So what I did was I added the variable 65, which is basically the proportion of individuals in a country that are greater than or equal to 65. I had my 4 levels of this density variable that I mentioned, with 0 being the lowest density. So all these this is the second highest, the third highest, and the fourth highest density. these variables are being compared directly to the lowest density variable. So that's why there's 3 of them. This is called dummy coding. You always have one less dummy variable than you have categories in a categorical variable. These are the interactions, and the interactions I ran were comparing this density variable multiplied by age. So this is an age by density interaction. In fact, it shows you that here, right? So there's this interaction 1 is for this first level, 100 to 199 population density times proportion above 64, it's called 65. So, well, what we find is that there are several statistically significant results. And when we look at statistical significance, the more mainstream way to do it is using an alpha 0.05 probability of a false positive result. And we consider anything that has a probability, if the what we call a null hypothesis or no result is true, we consider it statistically significant if it's below 0.05. If we were to raise our alpha to 0.10, this would be statistically significant here. So a couple of interactions. Now you'll notice also that this level here has an effect, and it's negative, and I'm not paying attention to that one because once you have an interaction that's significant, the other, what they call main effects, are not important to interpret. So I'm looking at these interactions here. So, but besides the interaction, we know that hospital beds has a negative relation to the case fatality. And the case fatality, I also log transformed it, so it's called log case fatality. We're using a natural log transformation. I didn't like the way the residuals looked across different levels of our predictor variables. So they're supposed to be homogeneous across different levels, and they weren't. So once I log transformed them, this was corrected. Everything else was fine. But we have these 3 effects, but we know that controlling for all these other variables, age, density, and these interactions, we do have a significant effect of hospital beds on this variable, right? On log case fatality. So there's a decrease. I believe I hope I'm right. It's 0.2378% decrease for each unit. Well, these are hospitals per 1,000, so each hospital beds per 1,000 increase. Okay, so this shows that there is an effect of the number of hospital beds per 1,000 on one's likelihood of dying. But there's interaction is also important. So there's this age by density interaction. So interactions are hard to tell without having some kind of a marker or a visualization here. So let's look at this. Let's try to visualize this. And this process statistical package, or they call it a macro. It actually provides a really nice visualization of an interaction. So what you'd have to do here is trace these lines going up here like this. So this is one line. So these are individuals who are in the 3rd category with the highest density. So as age increases, this group will tend to have a higher case fatality, but it's occurring in the highest density population. And this is being compared to the lowest density population. So we follow these little bluish dots here, circles. So you can see there's a big difference. Living in a highly dense population, a highly dense area, is much more detrimental than living in a lower density area for people who are above 65, because the greater the proportion above 65, the greater the case fatality. We also saw that there was an interaction that was significant at a value of 0.10, and that was this level right here. So it's between 2 and 299 in terms of density. That's people per kilometer square. So you can see that this one is also trending in this direction, in this upward direction, meaning a greater likelihood of dying if one is in this, as one increases in age, right? So as a proportion of the population increases in age, there's a greater case fatality. And that's relative again to the lowest density group. So it's interesting. And what does all this mean for us? It's telling us that, well, Oh, by the way, look at this R square. So this R square is a measure of the proportion of the variability in our dependent variable, our outcome. In this case, a log case fatality that is accounted for by these predictor variables. That's pretty good. It's 40%. I mean, 60% is unaccounted for, but that's 40% is pretty interesting and nice. But anyway, what this is saying is that this idea that preparedness, and again, I'm able to run these every day, but this idea, to see if this holds up, but this idea of preparedness may be play a big role in terms of determining who dies. I mean, countries that are investing more in terms of their elderly, like you see in certain countries here, like Japan and Saudi Arabia. I don't know where Saudi Arabia was down here. Maybe, I think it was Saudi Arabia or Germany. They're going to likely have a lower case fatality rate than the ones that are investing a little bit less in their healthcare of their elderly. This is very speculative at this time, but hey, we got some good data here. Need to run it on more countries. I keep on adding countries here. You can see I have a bunch of countries that I'm looking at, but we'll keep on. I'll make it better. Keep on making it better. But I got a decent number of countries here. At least the ones that have the most the most highest prevalence right now. Thank you very much for listening. Have a good day and be safe.